All right, hi everyone. Today I want to take the little time I have to very briefly motivate an ongoing research agenda of ours that to have a little more fun here, I've titled On the Quest of BFT Databases. In particular, I want to tell you a little bit about the system we built called Basil that we designed in pursuit of developing more scalable and usable transactional BFT databases. I want to start off our discussion by quickly revisiting the simple abstraction of a totally ordered ledger that is at the core of most BFT systems. It's a really powerful abstraction because it allows mutually distrustful participants, for example, Alice and Bob, to agree on common views of the system state, which in turn allows applications such as arbitrary smart contracts to materialize key value stores on top by totally ordering transactions in a way that trivially maintains traditional asset guarantees such as atomicity or isolation. Now, while this abstraction is both simple and powerful, implementing it in practice is in fact difficult. On the one hand, establishing a total order is hard. In the case of permissionless systems, you have to rely on techniques like proof of work or proof of stake, while in permission systems that I'm going to be focusing on today, you usually have to rely on a leader, you require multiple rounds of message exchanges, and recovery protocols are usually quite hard to reason about. On the other hand, while executing transactions sequentially is trivially safe, it not only requires you to limit transaction models to things like stored procedures or one-shot transactions that have to require knowing your read and write sets a priori, but it's not hard to see that sequential execution can easily become a bottleneck. Now, for most applications in the wild, this is an overly restrictive requirement because they often consist of commutative transactions. For example, Alice and Bob that are trying to buy a race car or dessert respectively are transactions that intuitively could have been executed independently. And this is by no means a new observation I'm making, and there's been a lot of work in the areas of sharding or directed acyclic graphs that have tried to address this, but are inherently limited in ways I unfortunately don't have enough time to explore or elaborate on. But at a high level, you can take away that sharding still requires you to have a total order within shards, while DAGs require you to do static transaction analysis, which limits the transaction model. What we propose instead in Basil is to take a page from our crash failure database counterparts, and instead of implementing totally ordered systems, implement executions that are indistinguishable from ones that are totally ordered. This is called the gold standard of crash failure databases. It's called serializability. And as part of Basil, the first question that we explore is how to actually capture this property in the presence of Byzantine actors. We end up defining the property that we call Byzantine isolation, which at a very high level states that, at least from the perspective of any correct participants, executions should look indistinguishable from any execution that is asset compliant. By asset compliant, I mean it maintains atomicity and isolation, even though transactions may not have been executed sequentially. The second agenda that we pursue in Basil is to actually revisit the requirement of leaders in totally ordered ledgers. Leaders are not only hard to elect, but they can easily become scalability bottlenecks because they have to totally order, they have to do the sequencing for all transactions, and they have to broadcast to all of their backups, which has sparked a lot of work trying to reduce these bottlenecks, mostly trying to solve this by using multiple leaders. But since that's a partially solved question, the question that we really want to double down on in Basil is the question of quantifying fairness. If you remember Yunna's talk from a couple of minutes ago, reasoning about fairness in Byzantine system or in ordering is a fickle matter, and it would be much easier if in fact we could just get around the whole problem. So that leads us to the second driving agenda of Basil, and that's a property that we call Byzantine independence. And in particular, the property that we would like to have from BFT databases or agreement protocols for that matter is that no group that consists solely of Byzantine participants can unilaterally decide the outcome of operation results. So for example, if you have a leader that leader has undue control over transaction orderings and can easily inject transactions for front running. But it applies to other parts of the system as well. For example, executing transactions in a way that doesn't allow Byzantine replicas, data servers, for example, to influence too heavily the outcomes or the read results of your transactions. So with these two guiding principles in mind, we designed a system called Basil that offers a replicated sharded BFT database that implements interactive transactions to offer a flexible application interface for developers. It meets both our requirements of Byzantine serializability and Byzantine independence, at least as long as the network is not strongly adversarial, in which case actually no system can provide Byzantine independence. On the performance side of things, Basil offers several desirable properties, including concurrent execution of transactions rather than sequential execution. It allows transactions to commit across shards in just a single round trip when there's not too much contention. It does so while maintaining linear communication complexity and avoiding the potential scalability bottlenecks, as well as the fairness ones of a leader. And lastly, but no less importantly, it allows transaction recovery to be fine-grained in the sense that transactions that don't conflict can complete independently, which is different from traditional leader-based system that actually have to stop all transaction processing when failures occur. We achieve all these properties by organizing Basil around the principle that we call independent operability. Concretely, in Basil, we empower clients to act as the coordinators for their own transactions, both for transaction execution and for the replication and distributed commit across shards. So on the execution side of things, we allow clients to speculatively execute transactions in parallel, but safeguard Byzantine serializability by enforcing a BFT robust variation of optimistic concurrency control. And on the distributed commit side of things, we take a page from existing crash failure databases and actually merge the layers of two-phase commit and replication to avoid redundant coordination that's often present in these layered systems. And I'll refer back to that in a little bit. To do so, we have to make some design concessions. And for one, we assume that clients are no longer anonymous end users, but rather application front ends. And additionally, we do have to rely on a slightly higher replication factor in order to actually achieve this desirable property of Byzantine independence. Now, what is skillfully swept under the rug in some previous slides is that despite the obvious flaws of a leader, it does offer the desirable property that actually guards the system from the influence of clients. And what I'm saying instead now is that we're trying to combine optimism with Byzantine clients, which is probably not hard to see is a slippery slope. And doing so safely and robustly in terms of performance is the main challenge that we try to tackle as part of Basil. At a very high level, without not going too much into this, we address this problem Basil by once again relying on our ethos of independent operability and roughly speaking, allow clients to handle recovery for their own transactions by finishing faulty transactions that block them. And importantly, as I mentioned previously, this recovery is local to each transaction and doesn't actually affect independent concurrent transactions. So it's nice and all that we designed the system and has a lot of desirable properties, but what we really want to know is whether that design actually translates to practice. So what we did is we implemented a prototype of Basil and we evaluated the performance using 3 common OLTP workloads that use interactive transactions and experience varying levels of contention. And by contention, I mean the probability that ongoing transactions actually conflict. This graph shows the peak throughput on these workloads. And on the left, you can see Basil in comparison to Taper, which is a recent state-of-the-art crash failure database that uses a similar client-driven design to Basil and also integrates distributed commit and replication. Our overheads mainly come from the fact that Basil has to rely on signatures and requires larger quorums to maintain Byzantine fault tolerance. But nonetheless, it offers quite competitive performance given the increased security. If we look to the right instead, we compare Basil against two BFT baselines that also both offer interactive transactions and concurrent execution, but unlike Basil, follow a standard modular approach where you lay a two-phase commit and concurrency control atop black box consensus protocols. In this case, we evaluated over hot stuff and PBFT respectively. And here you can see that Basil actually significantly outperforms both the baselines. And that's mainly because we avoid the redundant coordination during distributed commit, which allows us to commit in a single round trip. And this reduction of latency directly translates into quite significant throughput improvements on contention bottleneck workloads. Okay, it's great that Basil's performance is really good during gracious executions, but like I mentioned earlier, that was partially achieved on the back of the premise that we empower Byzantine clients. So to validate how robust Basil remains when clients actually misbehave, we specifically look at how Byzantine client behaviors can influence the transaction capabilities of correct clients rather than the overall system throughput. So one thing clients can do is they may stall their own transactions, which causes contending transactions to block. But the way Basil's recovery protocol works, it allows clients to very quickly in one round trip to themselves complete such transactions, and does so in most cases without having to actually abort and back off and retry by letting clients form redependencies on uncommitted transactions. A more difficult failure to handle instead is when clients attempt to equivocate proposals during distributed commit, which is a typical failure that happens in leader-based systems for replication. Here, the performance penalty is significantly higher because recovery is quite a bit more involved. But fortunately, Basil's design doesn't actually allow clients to choose what values to propose. And in practice, we can show that it makes pursuing the strategy more or less infeasible. So in this case, the throughput is completely unaffected because clients never actually manage to equivocate. Overall, we can show that despite more 40% of total transactions being faulty, which is disproportionately high in our assumed setting of a permissionless permissions setting, because we can punish and exclude clients that are misbehaving reliably, we can show that Basil not only remains robust, but it's also not only live, but it's also robust in performance, since failures only affect conflicting transactions. And when they actually do, clients are able to finish them quite quickly. And that's an important distinction that I've iterated a few times now compared to leader-based systems, where when a leader is under duress, you would actually have to halt all transaction processing. Okay, at this point, I want to end this very, very brief introduction. And given the fact that they didn't actually explain anything, I'd be surprised if you didn't have any questions or opinions for that matter. I'm not going to answer the perhaps most important question of why we named the system Basil, but you should feel free to ping me or email me offline if you want to learn more about Basil, and I'd be happy to chat in more detail. Thank you.